This is some of the studies that have been done to show, to understand why they are so resistant to proteases. So this is a three-dimensional structure of a chromatin-like protein, and it's so resistant because it had disulfide bridges from cysteines. So cysteine which folds the protein in a tight globular shape, which makes it inaccessible to enzymes to go in and then cleave it and so to break it down. So this is an option that is not available to winemakers, having an enzyme to break it. So as I mentioned before, you can bottle a wine, and if you fail to remove all the heat unstable proteins or all the pure proteins, this protein will be fully soluble in the wine. So they will be there, but they won't be visible. They will pass through the filters. However, with time, and especially with wrong storage conditions, so temperature fluctuations, for example, during transportation, these proteins can denature, they can become insoluble, flocculate, and then they can stick together, coagulate with each other, making this aggregation bigger and bigger, to the point that the gravity will do its course and they will sediment and form a hazy wine with a visible turbidity and also at times some sediment. Of course, this is something which is not acceptable for consumers, and so ways to prevent it are required. The main factor, if you want, that starts this process is temperature. You have to think about temperature in the lifetime of a wine. So when a wine is in the cellar, at cellar temperature, so 15, 14 degrees, 13 degrees throughout its life, there's no problem. The protein don't have a chance to denature. But when the wine exits the cellar and starts traveling the world, especially if the travel is very long and in things like in a shipment like this, the temperature can be quite extreme. There are some data that show that the wine inside one of those containers can go to 55, 60 degrees, the temperature of the wine. What we've been researching a lot in the past decade or so is to try to understand the behavior of the main proteins responsible for this instability. So we talk about chromatin-like proteins and chitinases. So these have been purified and they've been submitted to an analysis which basically it consists in applying increasing heat to denature it. So when the temperature reaches a certain temperature, like for example 61 for TLPs or 55 for chitinases, there's a peak. That means that the protein is unfolding, so the three-dimensional structure is open up, it's kind of lost. Then you cool it down and you heat it again. In the case of chromatin-like proteins, when you heat it again, you have another peak. That means that the protein refolded, so came back to a original or sort of original three-dimensional structure. For chitinases, this is not the case. It unfolded, you see the unfolding ones, and then when you cool it down and heat it again, this does not happen. This is a proof that chitinases are the main protein responsible for haze formation, as confirmed by many other experiments. This is an important piece of information for the part that will follow on the test for prediction. So in the past, we have taken a naturally turbid wine like this one, we've centrifuged it, and we separated the total wine from the supernatant and the pellet. So the P line here only includes the protein that precipitated out, so the things that got insoluble over time. So what's in there? In this natural haze, we find occasionally a bit of glucanases, always chitinases, and sometimes chromatin-like proteins, sometimes not. So this is what we're dealing with. These are the proteins that are responsible for haze formation. So this and many other experiments have been combined to come up with the current agreed method or mechanism for protein haze formation in wine. So this is what happened. We have proteins in native state, so soluble protein that in a wine, the wine appears clear, pure proteins. And then the first step, so the protein unfolding and sometimes refolding happens. So this is a temperature mediated step. So with inappropriate storage condition, protein can unfold, the red line. And if the protein are stable, like the chromatin-like protein that we've seen before, this is a temporary state. And then when the wine becomes cooler, the protein refold. So it stays soluble, it doesn't aggregate. So there is no way forward for stable proteins. But the unstable proteins, the chitinases, and also some class of chromatin-like proteins, they cannot go back, as we've seen in the graph graphs before. There's unfolding in one go, and if you do it again, it doesn't refold. So that is a one-way route, which brings to unfolded protein. Once a protein unfolds, it opens up. It shows the hydrophobic binding sites which are inside the core structure of the protein, and this, by hydrophobic interaction, can attract other unfolded proteins, so the protein can start self-aggregating, so becoming a bigger aggregation. At that stage, the wine composition also plays a role, because this hydrophobic attraction leads to small aggregates that, to grow, they need to be cross-linked by, for example, the presence of sulfur, of salts, of metals, other wine components. Also, the wine composition has a bit of a role. So this is what is called the aggregate cross-linking. And this is the final step, where the aggregates become large, and as such, the wine is perceived as turbid. So this is basically where we are at. So some